Assalamu alaikum. Can you all hear me? Can you all hear my voice? Okay. Okay. This session will go on till 10 p.m. So that's when we'll end. Somebody was asking. But it's up to you. If you want, you can leave earlier as well, and uh, I'll upload the class on YouTube so you can watch it later on as well. Is the screen visible to everyone? And is this screen like good, or is the resolution too low? Okay, so let's start. In our last class, the last session, we did some questions regarding forces. So these were like the most of the type of forces about a person who's parachuting. So what are the forces that will be acting on him? His weight, air resistance, how do they vary as he falls, and when does he reach terminal velocity? When he opens a parachute, what happens? So that's all what we discussed in last class. And then if there's a car which is traveling, so what are the forces on the car? For example, this question outlined all the four main forces that would be acting on a car, which would be the driving force, which is the forward force by the engine. Then there's air resistance, which would be opposing this motion. Then there's the weight of this car, and then a contact force due to this weight by the earth. Uh, so that was what we did, and now we ended the last class before with the question of circular motion. So we'll be completing or moving on from that part. So this is the question on the left that we did. So I'll be moving on, and we'll be doing these two questions. And just like once we're done with these, I'll move on to the next part, which is moments or turning effective force or torque, whatever you guys call it. Okay, so in this part, they're asking me the satellite travels at a constant speed in a circular orbit. And by the way, feel free to ask questions however you want. You can use your mic, and you can also ask questions through the chat. Totally up to you, whatever is convenient. I'm okay with all of them, but I would appreciate if you use the mic because that makes the class more interactive. So the satellite travels at a constant speed in a circular orbit. Underline the quantities in the list below that are scalars. So this question is, although this is part of circular motion, but this part is not circular motion. So this is asking me about the quantities which are scalar. And if you've like studied the syllabus well, we know mass is scalar, we know the speed is scalar, and acceleration, force, and velocity. All the rest are vector quantities. So that's what you know. The next part, state what is meant by velocity. So we know what velocity is, rate of change of displacement. Explain why velocity changes. So the question, the thing they're asking me about is the velocity of the satellite is changing. Velocity is changing, but the speed is constant. How is it possible? That's what they're asking me in the second part. That how is it possible that despite the speed being constant, the velocity is changing? So the answer to that would be that the answer to that would be that velocity is not like velocity is a vector quantity. So there are two things involved in a scalar quantity. One is the magnitude and one is the direction. Either of them, either of them changes, the quantity changes. So the magnitude is constant, which is speed, it's constant, but it also has a direction. So the direction of velocity is changing, and because of that, and like since it's a vector quantity, because of its direction being changed, the quantity changes. So that's why velocity is changing, because it's changing in direction. And we know this if I like mark this point, the velocity, let's say, if it's moving in a circular motion like this, so the velocity at this point would be to the left, and once it travels downwards at this point to the pink point, the velocity would be to the right. So obviously the velocity, although the speed is constant, so the red line could be positive 5, the pink line is also 5 meter per second, but it's in the exact opposite direction. So this change in direction uh, is why the velocity is changing. Next part, explain what makes the satellite move in a circular orbit that is circular. So we talked about this in last class as well. The cause for circular motion is always a centripetal force. And right now, what they're asking us is what causes the circular motion. So we need to mention centripetal force, and then we also need to mention the cause for circular motion. Okay, so Hussein is saying that आवाज नहीं आ रही, बाकी सबको आवाज आ रही है या सिर्फ हुसैन की तरफ कोई शोर है? बाकी सबको आवाज आ रही है मेरी? जी हुसैन, कुछ स्टूडेंट्स कह रहे हैं उनको आवाज आ रही है, तो प्रोबेबली आपकी तरफ कुछ इशू हो रहा होगा, तो आप इसको चेक करना। ठीक है, ओके। सो कमिंग बैक, अगर कोई सवाल हो आप लोगों का तो पूछ लें, और अगर समझ आ रहा हो तो भी मुझे बता दें ताकि मैं अपडेटेड रहूँ। बेसिकली मकसद आप लोगों को समझाना है, मेरा सिर्फ बोलना नहीं है, तो इस हिसाब से। Okay, so we did this part in the last class as well. That so you need to mention two things. One is the centripetal force, which is always the cause for circular motion, and the second one is what is like the centripetal force here right now. So the centripetal force is the force which acts to the center, and obviously this time in this case it's the gravitational force as we did in the last part. So that would be the answer. Now the next part, or you just try doing this part yourself, because like we've covered all the basics in these two questions. Like whenever there would be a question of circular motion, it would either be something related to what we'd done in the first two questions. So mark this part, October November 2018 variant 2, and try doing it yourselves. Okay, and this question now, this is I found this question to be very important. It kind of underlines the concept, or a good gives us a good understanding regarding this whole chapter of forces. And this will be the last question we'll be doing, and after that we'll move on to circular motion. Okay, so figure 2.1 shows a man of mass 80 kilograms standing in a lift elevator. The gravitational field strength is 10 Newton per kilograms. Calculate the weight of the man. So for the weight, we know the simple formula. Weight equals mg. So that's the formula that we know. We apply the formula. The mass of the person is 80 kilograms times gravitational field strength, which is 10. So the mass comes out to be 800 Newton. So the weight comes out to be 800 Newton. The next part, the lift accelerates upwards uniformly at 0.5 meter per second. Calculate the resultant force upward on the man. Now, this question is like a bit important. We know this formula, F equals ma. This is the formula you all know and you've all been applying. But one of the very important things about this, which like if you know this, then you have a better understanding. Good, you already have the understanding required, and if you don't, then like pay attention. This F is the resultant force, is always the resultant force. It's not just some random force acting on the object. There can be times where there could be multiple forces acting on the object, but what we use in this formula is F equals ma. So for example, if there was a box like this, and there was a force acting towards the right and a force acting towards the left. So let's say this is 10 Newton, and let's say this is 5 Newton. So if I know the mass of this block, which is let's say 2 kilograms, and I need to apply the formula, which is F equals ma. So I can't just like use any of these forces and find the acceleration. To find the acceleration, I need to use the resultant force. So resultant force meaning I would need to do the vector addition, which is 10 minus 5, which would give me 5. So I could say 5 equals mass times acceleration. 5 over 2 equals acceleration equals 2.5 meter per second square, and I could say acceleration is in this direction, which is equal to 2.5 meter per second square. Meter per second square. Okay, so this is like how we do this. So in this question, they've asked me about the resultant force. So this formula is always force resultant equals mass times acceleration. So coming to this question, calculate the resultant force upwards on the man. Now we need to find the upward resultant force on the man. Uh, we know the acceleration and we know the weight. The best part about it, like the part which could confuse some of you is the upward force is not equal to weight. It's not supposed to be equal to weight. The upward force is the resultant force, which is coming about as the resultant of is coming out when we add some forces, but it's not equal to the weight. So for this, we apply F resultant, which is equal to mass times acceleration. We know the mass of the object, and they've told me the acceleration. The acceleration is 0.5 meter per second. So I multiply it 0.5 and I get my answer. It comes out to be 40 Newton. So, uh, sorry, yeah. So it comes out to be 40 Newton. So 40 Newton is the upward force acting on the object. It's not equal to the mass, it's totally unrelated to the mass. Now, the next part, the force exerted on the man by the floor of the lift. So, what's the force that the lift is the uh, floor of the lift is exerting on the man that's causing this acceleration? So, just how I did this part, we're supposed to do this part as well. So, this time this was horizontally, and now if I make this part vertical and I say this is 80 kilograms, just a second, I'll write this in a better way. This is the lift where the man is. He has a mass of 80 kilograms, and there's this force acting downwards, which is the weight of the object, which I know is equal to 800 Newton. So there is also another force, which is what they're asking me in this question, which they've called the force exerted on the man by the floor of the lift. I don't know this force, so I just say this is F. And I know the acceleration of this object is upwards and is equal to 0.5 meter per second square. So I just do what I did in this whole part where I like outlined this to you. So I could say the F resultant. What's the F resultant? I've also found the F resultant on the object, which was in the last part, is equal to 40 Newton. So I note that the result of these two forces would be 40 Newton. Like these two forces, the result of these would be 40 Newton, which is giving me an acceleration of 0.5 meter per second square. So I just simply do this, like F resultant equals 800, or F resultant equals F minus 800. I do this. I know F resultant. I just found it out and it was equal to 40 equals F minus 800. I rearrange F and I get 840 Newton is the force exerted by the floor. And I write equals 840 Newton. So this is what I get. And if you like do what we just did in this previous part, where I just explained this to you, you'll realize that this is giving me the like the right answer or the accurate results. So this is how this is supposed to go. So I hope this is clear to you, clear to everyone. If anyone has any questions, feel free to ask. Otherwise, we'll proceed with the next part, which is torque. Clear to everyone? Yes, I will upload the recording. Okay, so thank you. So I assume everyone else also understood it correctly. Okay, so now moving on to the next part, which is torque or moment of forces. So the question is, a student places a meter rule on the edge of a triangular prism. The prism is used as a pivot and the rule balances about the 50 centimeter mark. So you can all read this question statement. They've just explained this diagram in words. So that's all they've done. So the next part, uh, the keywords are in this part is the rule balances again. Okay, so keep it for now. So we'll read this question. A student places a meter rule on the edge of a triangular prism. The prism is then used as a pivot and the rule balances about the 50 centimeter mark. So It balances when there was nothing involved, nothing on this scale. It balanced about the 50 centimeter mark. What this tells us about this whole thing is its center of mass was on the 50 centimeter mark. So this is what this tells us. This is why they've written this whole statement. So if like they ask the question separate differently, they ask you like they give you this statement and they tell by they ask by that by reading the statement, where's the center of mass, where could the center of mass of the object lie? So how do we do this? We know that if it's balancing on this point, it's as if the whole mass is concentrated at that point. So that's why we call it the center of mass. The student then places a block of wood at the 10 centimeter mark on the rule and an empty measuring cylinder at the 80 centimeter mark. The rule is balanced. The rule is still balanced. The arrangement is shown. So the amazing part about this, like I'll go step by step because the next question is also again something similar, and this is like the gist of the questions they'll ask you in this part. Okay, so this part is the student then places a block of wood at the 10 centimeter mark on the rule and an empty measuring cylinder. So now they've balanced. So meaning that the weight of this empty cylinder was causing a torque. The torque was clockwise. The torque was clockwise because it was moving this uh, rule in this direction, which is the clockwise direction. This is my clock, 12, 3, 9, and 6. So since it was moving the ruler in this direction, I would say this is clockwise. And this block of wood was moving the object in the other direction. So I could call it to be counterclockwise. So clockwise and counterclockwise, these are the two directions, these are the two moments. So if the rule is still balanced, it means that this clockwise moment equals the counterclockwise moment. So like this was just for your information. The next part, the student now places a weight of 0.9 newtons on top of the on top of the block of wood. He then starts to pour oil into the measuring cylinder. The rule balances again when there is 60 centimeter of oil in the measuring cylinder. So the student poured oil into this measuring cylinder until it reached a height of 60 centimeter square, 60 centimeter cube. So like let's say it reached this point. So when it reached this point, this was whole filled. It balanced another mass, which they've told us. The student now places a weight of 0.39 Newton on top of the wooden block. So there's this another mass, which is 0.39 Newton. And this balances when there is like 60 centimeter cube of oil in this part. Meaning now again the clockwise and the clockwise counterclockwise moments were equal. So what we now do is the next part is calculate the weight of the oil in the cylinder. So for that, what we do is we write clockwise and counterclockwise. So we make a chart. We make like a table. We write the clockwise moments. So there was this clockwise movement by the wooden block, which was being equaled by the measuring cylinder. So it's as if since both are being equaled, so I can just simply ignore them. I don't need to like use them in my calculations because in the end, what I'll be doing is I'll be equating the clockwise moment equals counterclockwise moment. That's how I'll be equating. But when they're both equal, so I can just simply cancel them out. I hope this part is being clear. If anyone does not get this, do ask because it's important. So what I do this in this part is I simply ignore everything else and I just know the torques, the two torques. So there's this one torque which was by this block which I now added 0.39 Newton. It's counterclockwise, and this block is at a 40 centimeter distance from the center. So the torque on this pivot, the pivot which I've made in red, so the torque would be 40 centimeter. To convert it into meters, I divided by 100 times 0.39. Can someone tell me what the answer would be? So this is how I'll get the counterclockwise. Just write the answer and I'll write it down. For clockwise, I know that there's this weight of the oil in this cylinder that is causing this, because before the weight, everything was equal. So I don't need to consider that part. Weight times this distance. So this distance, I know it's equal to 30 centimeter. So 30 centimeter. Can anyone tell me the answer? This would be 0.3 W, and the other one would be 0.156, 1.6 Newton meter. So these both are supposed to be equal to each other. So that's what I do. I equate the counterclockwise moment 0.156 Newton meter equal to 0.3 W. I do this equation and I find W. So W would come out to be 0.156 divided by 3. W would come out to be uh, 0.52 Newton. So yeah, that would be my answer. This would be my weight. So this is how we'll do this question. We'll ignore everything else. We are now ignoring the mass of this block. We're ignoring it. Why? Because the mass of this block was equal to the mass of this measuring cylinder. So that's why it's being equal. And similarly, there's a mass of this meter rule to the right, and then there's another mass of this meter rule to the left. But since both are equal to each other, they're canceling out, so we don't count them. And even if we did, like for example, they had a value of, let's say, the block of wood was causing a torque of 10, 5, and similarly the measuring cylinder, the torque, the counterclockwise, the clockwise torque by the measuring cylinder would have also been equal to 5, and let's say the mass of this meter rule was equal to 15. So 15 would have come on both sides, so they eventually cancel out. So I don't need to add these things. So that's why we're not adding. This is a very important point. Do keep this in mind. So that's how we end up with the weight of the cylinder. Okay, so I'll now be proceeding with the next part. But as I had informed in the last class, we'll now have a 10 minutes break for Isha because I need to head to the masjid. So we'll resume at around 9:10, inshallah. Okay, so that's when we'll resume. अस्सलाम वालेकुम। सबको आवाज आ रही है मेरी? Is my voice good? Okay, so let's continue where we left off. So we were able to find the weight of the oil in the cylinder. Next part is find the mass of the oil in the cylinder. So obviously it's a very straightforward question. We know weight equals mass times gravity, and in this part specifically, we just know the we know the weight which we just found out, which is equal to 0.52, and we also know the gravity which is 10. So this would be equal to the mass, and the mass turns out to be 0.052 kilograms. So this would be my answer. The next part is calculate the density of the oil. So this time I just need to find the density of the oil. So the formula for density, if you all could recall, is density equals mass per volume. So density is mass per unit volume. So I know the mass. The mass I just found out it was equal to 0.052, and this mass was occupying a volume of 60 centimeter cube. So the conversion. Now this part is also important. How do we do these conversions? So I know 1 centimeter is what 1 centimeter equals, or let's say another way to phrase it would be, I know that 100 centimeters equal 1 meter. So if I now square this whole thing, so this would be 100 square centimeter square equal 1 meter square. So this is basically how we do our conversions. And now if this is cube, so I could say 100 cube centimeter cube would be equal to 1 meter cube. So this is how I do these conversions. And now from this, I know that 1 centimeter cube, if I like rearrange this, I'd get 1 centimeter cube equals 1 over 100 cube meters. So this is the conversion for centimeters to meter cube. So I could write my answer this time in two ways. One would be I just divide this mass, which is 0.052 divided by 60. 60 is the volume. So volume in centimeters cube. So when I do this, I get an answer which is equal to 0.867 times 10 to the power negative 3. Now the units are also important. I would say kg per centimeter cube. So this is how I would write if I need to write my answer in centimeter cube. I just simply divide it by 60. But if the case was a bit different, if it was not like this, so then what I do, then I would need to convert this thing into meters. So I just found out that 1 centimeter cube was equal to 100, 1 over 100 meter cube. So this was my conversion. So I could similarly say 60 centimeter cube would be equal to 60 divided by 100 to the power 3 meter cube. I just multiplied both sides by 60. So this would be my conversion. So I would use this thing, and instead of 60, I would write this thing here, which would give me something 0.052 divided by 60 over 100 cube. My density would this time come out to be 867 kilograms per meter cube. So this is how I do this. If I just write what I just did, density equals mass over volume equals 0.052, which is the mass, divided by the volume in meter cube. So it would be 60 over 100 to the power 3. I do this and I get 867 kilograms per meter cube. So this is what I simply get. I hope this part is clear to everyone. If anyone has any questions, feel free to ask them. So this is how we would convert when if there was a need for conversion. This is how the conversions would go, and depends on how I write my answer. If I just divide it by centimeter cube, then the units should be kilograms per centimeter cube. And if I convert it into meter cube and then do the part, then my unit should be kilograms per meter cube. So this is how we do this question, and this is also like a standard type of question. If you're able to solve this, you have a good understanding about this, you can easily solve the questions that follow or those that come after this. Okay, so moving on to the next part, and this question is again very similar to the previous one. So obviously I won't be doing this whole thing again, or yeah, I won't do this whole thing again. So like maybe just mark this question somewhere. I'll just give an overview how we're supposed to do this, and you can solve this later on. So the student places this 50 centimeter mark of a uniform meter rule on a pivot so that the ruler balances. This tells us one thing. One very main thing is that the center of mass of the ruler lies at the 50 centimeter mark because it's balancing on both ends, meaning the mass to the right and whatever the moment is, the mass to the right is causing is equal to the mass to the left as well as the moment, all the moment that's to the left. This is essentially the definition of center of mass, which is a point where the whole mass of an object could be assumed as being concentrated. So that's basically the idea behind this. So the next part, he then places the cube on the rule meter on the rule with its center of gravity directly above the 75 centimeter mark. A mass of 0.50 kilograms is moved along the rule until balance is restored. This is shown in figure 1.1. The rule is balanced when the 0.05 kilograms 0.050 kilogram mass is at this 10 centimeter mark. Calculate the mass of the cube. So obviously there's a moment because of this cube, and there's a moment because of this cube, this mass. So the moment because of the cube is the clockwise moment, which is supposed to be equal to the counterclockwise moment due to the mass. So we equate both moments, and basically the equation would come out to be something like uh, 0.050, which is the mass, times gravity, which would give me the weight, times the distance, times this distance. And remember this distance, don't go like they've told us it's at the 10 centimeter mark. So just don't use the 10 centimeter value. Rather, just think for a moment that my pivot is at the center and it's the 10 centimeter mark. So the distance from the pivot to the mass is would be 40 centimeter rather than 10. So multiplied by 10 equals, this is the moment on the left, which is the counterclockwise moment. It is supposed to be equal to the moment on the right, which would be weight of the cube times the distance of the cube. So they've told us that the cube is at the 75 centimeter mark, meaning 75 centimeter from the 0 centimeter mark, and which means this would be equal to 25 centimeters. So if this is 25, then I could simply say weight of cube times 25. And I don't need to convert this 25 centimeter to meters right now, because whatever conversion I would do here, I would divide this by 100, and I'd also have to divide this on the right side by 100 as well. So when there's the same thing on both sides, it just cancels out. So there's no need to do this conversion. You can do them if you like, but it'll just only make the calculations a bit more tedious. So I have this, you can now equate, you'll find the weight of cube, which would be equal to the mass times gravity, divide the weight by 10, you'll get the mass. The next part is the cube has a volume, determine the density of the cube. So we just found out the mass, which was equal to whatever the answer was. Mass divided by volume they've given us. This is the volume, just divide both of them and you get the answer. That's how the part is supposed to be done. Do try solving this yourself later on. It's October, November 2011, variant 2. Yes, just a second. Okay, so again, this part is again a very important question, this and the one that follows. So these are like the two very important questions. If you can solve them, this was a type of question that comes. There would be this ruler, and they'd be asking us that how it balances out. The next type of question is another type of question where the moments, we use the moments to find different sort of stuff, whatever they ask us. Okay, so you all can read the question statement for yourself. Shows a firefighter of total weight 840 Newton in equilibrium at the top of a ladder that is pivoted at point P. So the ladder is pivoted at point P. They've made it very easy. We don't need to now deduce anything. We can just simply assume that the pivot is point P, and therefore all calculations, all those distances would be at like have this distance would be from point P. The ladder leans towards a burning building at an angle such that the center of gravity C of the firefighter is 12 centimeter above and 5 centimeter to the right of P. The firefighter holds a hose that directs a high speed jet of water horizontally into a burning building. Calculate the moment m of the firefighter's weight about P. So they're just asking me about the moment because of this firefighter's weight at the moment because of this weight about this point P, about the point P, which is in purple, about this point P. So obviously, I just simply apply the formula. The formula was sorry, not force. The formula was torque equals force times distance. So that's basically the formula. And yeah, so that's basically the formula. And the distance, this distance is, it's not distance, it's actually displacement. And how we define this displacement is as being the perpendicular distance between uh, the pivot and the line of action. So my line of action is W, is this whole line which they've made, and pivot, the perpendicular distance between this line of action and this pivot. So this is what I need to find, the one in blue. So this is what I know, it's equal to 5, and I know the weight they've given me is equal to 840 newtons. So I can simply write torque equals 840 times the distance, which is 5. So I'll get what, 4200 Newton meter. So that will be my answer. That will be the torque or the moment due to the firefighter's weight about point P. The next part, the jet of water causes a horizontal force R on the firefighter that acts towards the left through C. So I'll now erase this part, and now there's this another force acting due to this towards the left at C. So this is the force which they've called as being R. So this is for force R which they've mentioned in this part. Now calculate the size of R that on its own ensures that M is exactly cancelled. So this moment, the moment which we calculated or here right now was equal to M. This was M because that's what they've asked in the question. So this is equal to M, and this R should be such that it cancels out M. The trick about this is like previously in the previous question, both forces were vertical. All these forces are vertical. This time there's this force W which is horizontal, vertical, and then there's this force R which is vertical. So there are like two different forces involved right now. So obviously a solution like this could be the little bit of trick whatever is there they'd ask me to here. Okay, so how do we do this? I know R, or the moment due to R, is supposed to be equal to 4200. So torque equals 4200, which is equal to R times the perpendicular distance between the line of action and the pivot. So this time my line of action becomes this. This time this becomes my line of action, and this becomes the perpendicular distance between the pivot and the line of action, which they've already told me as being equal to 12. So I know this. equals r times 12. So I can just simply divide the other side by 12, and 4200 divided by 12, I'd get 350. R would should be equal to 350 Newton. So that's all what they've asked in this part. So I hope this is clear. If anyone has any questions about this, like feel free to ask them. Okay, so just a third force that has a turning effect about P on the ladder. Now they're just asking me about any third force that could have an effect on the ladder. Now if I like this is up to us. How did we get the 12? They've given me this 12 here right now. This 12. This 12 is the perpendicular distance between the line of action. The line of action of R, I've like made it in yellow, and the perpendicular distance between the line of action and the pivot is this blue line, which is equal to 12 as they've given me. So that's how I got 12. I hope that's clear. Okay, so this is a third force that has a turning effect. Okay, so this answer is up to us, is up to the student. As long as the answer is something reasonable, it's good. One thing which I would say is the weight of the ladder, because we've just ignored this whole weight. The weight of the ladder, let's say it has a weight something, so it would have a center of mass somewhere around here. So if this is the center of mass, so like as you could see, the center of mass would be causing a clockwise movement about P. So this is what we've ignored. So this is the third type of force which could have a turning effect about P, but we've ignored this. So this is part. Okay, so the next part is about radiation. So I'll be skipping it because that's not what we're doing right now. So I'll just stick with what stick with the topic we're revising. Okay, so moving on to the next question. Explain what is meant by moment of a force. So it's the moment of a force is the turning effect produced by a force about a pivot. So you can answer that accordingly. This is the important part. So the calculation involved right now would be a bit like this is all about this topic. If you're getting this, you know how to solve these questions. You'll probably be able to solve almost any question that you get in the exam. So shows a system for raising a heavy piece of metal into a vertical position. A man pulls on the rope with the horizontal force T. So this force they've told me is T. The piece of metal has a weight of 2000 Newton and is freely pivoted at A. So it's pivoted at point A. Just a second. Okay, so the piece of the metal has a weight of 2000 Newton and is freely pivoted at point A. The system is in equilibrium. So it's pivoted. So now they've also made my work easy. They've told me what the pivot actually is. So now I don't need to think something. And obviously, if even if they didn't tell me, I could just tell it by looking at the diagram that A might be the only point that could possibly be acting as the pivot. All the points are something very different. They can't be pivots. Okay, so by taking moments about A, so by taking moments about A, calculate T. So now I need to take the moments about A, calculate T. So this is just like the previous question. There are two moments involved. One moment is the clockwise moment because of this force. So this force has a line of action. Uh, the line of action of this force is this. And this line of action has a perpendicular distance with the pivot equals 2 meters. So if I draw this diagram and I write clockwise and I write counterclockwise, so this force gives me a clockwise moment, and the moment would be 2000 times 2, it should be equal to 4,000 Newton meter. So that will be my moment, the clockwise moment. And then there would be a counterclockwise moment. So this counterclockwise moment uh, would be this force T. So this force T, I'll now use, I think, different colors. So this would be the line of action of force T and the pivot. So this could be the perpendicular distance between the pivot, or better to draw it here. So this would be the perpendicular distance between the pivot and the line of action, which they've told me to be equal to 8. So what I do is 8 times T equals to like 8T. That would be my counterclockwise moment. And since they've told me that the system is in equilibrium, the counterclockwise moment must be equal to the clockwise moment must be equal to the counterclockwise moment, and I could accordingly write 4,000 equals 8T. From this I would get T equals 500 Newton. So I would be able to find T just by this. So this is important. This is a bit different from the previous the scale questions. On the scale questions, the only forces acting are vertical forces on a horizontal scale. This time the speed of metal is at an angle, is making an angle with the ground, and there are two forces involved. One is horizontal and one is vertical. Both are causing different type of moments. So I hope this part is clear to everyone. The force T and the force that the rope exerts on the man are related by Newton's third law. State the relationship between these forces. So there's this person, the force T and the force that the rope exerts on the man. So obviously there's this force that the person is pulling. The person has had the rope in his hands and he was pulling the rope. So the person, when he like pulled the rope towards him, uh, what they're asking us about is the force T. The force T is a pulling force, which is the pulling force by the man on the rope. The force T and the force that the rope exerts on the man. So by me pulling the rope towards myself, the rope is by Newton's third law giving or having a reaction force on me. So when I pull the rope is also pulling me. So that's what they're asking me about this, the relationship between these forces. So how would these two forces relate? Obviously, they've told us it's Newton's third law. So obviously, their action and reaction forces. And obviously, when I'll be pulling a rope by Newton's third law, when I like pull the rope and I apply a force towards the left, there's obviously a force to the right on the person who's pulling it. So how are they related to each other? They're equal in magnitude, opposite in direction, and on different objects and of the same type. So on different objects, one is force on the rope by the person, and the other one is force on the person by the rope. Rope by person and person by rope. Force on rope by person, force on person by rope. So the object which are experiencing the force are different, and the object which are causing the force are different. They equal in magnitude and opposite in directions. So I hope this is clear. So this is the next part, and obviously I would like to leave this part to you all to do it yourself. So you can mark this question, May June 2013, variant 1. So this is similar to the two questions we've done above. These two questions with a little bit of trick. These two questions. This is similar to these two. Okay, so this question is again something like, so we'll do this. The weight of the student is 600 Newton and this force acts downward from the center of mass. Explain why the student does work as his body rises from the ground. So why is the student doing work? Obviously, this is not part of it, but I'll just simply tell because it's a 1 mark question. Uh, Work done is force time distance traveled in the direction of force. So when he pushes the ground for the push up, so his body rises. He travels a distance. When he pushes the ground pushes him. By Newton's third law, the ground is pushing him upwards, and the force which is upwards on him by the ground causes his body to move upwards. So there's a force and there's a displacement in the direction of force. So that's why there would be a non-zero value for work done, and then that's why the student does work. Set the form of energy that the student uses to do work. So whenever there are humans involved and they're like doing some work, it's always chemical energy being converted into other forms of energy. The next part, as a position at the position shown in figure 2.1, the student is stationary. The weight of the student causes the moment about his toes. So about his toes, they've now the moment about his toes. This keyword was enough to tell us what the pivot would be or what we're supposed to take as the pivot. So we take this point as the pivot. Now this is asking me to calculate the moment of the weight of the student about his toes. So because of his weight, I know the mass, I know the weight, the moment because of this. So you can just do it yourself and calculate the value of force F. So obviously, the moment due to the weight is counterclockwise, and the moment due to force F is clockwise. So when the student is stationary, as they have told me in this part, so the counterclockwise moment is supposed to be equal to the clockwise moment. I paid both of them, and I'll get my answer. Okay, so now, like I'll do this, and the next question would be about center of mass. State what is meant by center of mass. So, like I've mentioned this a couple of times earlier, and I think you all know this as well. So, center of mass is the point on the object where the whole mass of the body could be assumed to be concentrated. So, it's a that's how we define it. Or just to explain this in words, it's the mass. Where I could assume the whole mass to be. So, for example, if I have this bottle in front of me, and there's this point which I use, and I like use it to hold this object in front of me. So I could assume that the whole mass is concentrated some point in the center of this object. So that's just what the center of mass is. And some of the characteristics of the center of mass is that at the center of mass there is no resultant moment. So if you like lift an object from the center of mass, there would be no turning effect. So that's why this term is important, and the whole mass would be at that point. This is clear. The next part is state two features of the design that make the car stable. So any two features of the car that are making it stable. So like they could be a lot of like features. One of them is that the car being stable. Now, okay, so another part, the sport car is designed to be very stable when turning a corner at high speed. So how two features that make the car stable. So one of the feature would be that if you could look that his center of mass is towards it's not in the center, like it's not in a line which is at the center. So because of that, when he's like cornering, so there would be like if his mass if I'm doing a turn like this, and my most of my mass is concentrated at this point, so there would be the centripetal force which would be pulling me at this point, so there would be any such like moment which would like topple the car. But if like the center of mass is located at some point over here, and the car is moving in this direction, like it's moving it going at it, it's like turning, so there are chances that the car might topple over. The toppling over would be from this end. The car would topple over like this. If the mass is concentrated over here in the beginning, the car wouldn't topple over. The mass would prevent it, because most of the mass is here, the moment at this point could be greater. But if the mass is concentrated at this point or as far away from this end, so it would the more the chances are for it to be toppling over. And another reason for this, like make the car stable, like it's like up to you, there should be any suitable answers. So another reason could be that uh, the tires on the back are mostly, or if I leave this point, the surface area of the car is also quite great. So the surface area is a lot, and because of that, when the surface area is greater, the mass is divided, or the mass of the car is divided over a very large surface area. So whenever that's the case, the object is stable. So that could be a reason. Now, the next part, which is actually important, shows an irregularly shaped piece of card. It describes how to determine the position of the center of mass of the piece of the card. So, how do we do this? We just need to determine the position of the center of mass of the piece of the card. So you need to explain this whole experiment, and maybe since many of you have done the ATP, so you might have an idea about this. So a way could be that we make some holes on this card. So I'd make a hole, for example, at this point, and I pin this point, and I let the card like hang at this point. The card would hang at some point, and then I'll make a horizontal line downwards toward on the card and like this. So I'll just mark it. And then I would use, like, for example, if this is my phone, I pivot this point. Uh, I use this point, I make a hole here and I pivot it. So I'll get a line like this. The phone becomes like this. So what I do is I mark a horizontal line like this downwards, which is horizontal. So I mark this line. Then I move my point to some other point now like this. This time I make a hole and I pivot it here and I mark this horizontal line like this. So for example, the next hole was here, and when it was like the card was hung, the line was like this. Doing it twice is enough, but you could also do it a third time as well. So if I do it a third time, let's say like this, and I like hung this phone again. So this again gave me a line like this. So the intersection of all these three lines basically locates me my center of mass. So that's how you're supposed to find the center of mass if they ever like ask you in your exam. There's another question. I don't like plan to do this whole question because this is related to weight gain as well. What I will do is this last part, which is on each fence in figure 8.3, mark with a cross the center of mass. So we need to mark the center of mass on each fence. So what I know is if it's a square shape with uniform density, whenever that's the case, it's they've told me that the density is uniform and the shape is square. So I look for line of symmetries. So obviously when it comes to a square, it's the exact center. Like that's how we do it, like leave the line of symmetry part. But there's also another way, like for those who would like to do know the advanced way of finding these, we make line of symmetries. One line of symmetry for the square would have been like this is not part of the syllabus, this is just something I'm telling you from my own. Like this can help you if you've understood everything, then like pay attention, otherwise just leave this part. And this would be another line of symmetry on the square. So there would be two lines of symmetry, and the point where they intersect is my center of mass. So leave this part, but if it's a regular shape like square or a rectangle or a circle, the center of mass is at the exact center. The next shape, obviously, the key feature about the center of mass is if I look above the mass above the center of mass, and the mass beneath the center of mass, they're both supposed to be equal. And volume is also supposed to be equal. So if I look at this time this has an irregular shape. So if the center of this shape was supposed to be in red, the center of mass would be somewhere below this, as somewhere below this point red. If red is the center, like the if I find this distance to be equal to, let's say, 10 meters, then this point red would just be equal to 5 meters. So this is what red is. That's the center of the shape. The center of mass would be beneath this because the mass above the center of mass and the mass, or let's say the volume above the center of mass must be equal to the volume beneath the center of mass. That's only possible in this case. So the next part, explain why a wider base makes the fence more stable. Why the wider base makes the fence more suitable. So wider base, this is exactly what I said in this part. But in the previous question, they just asked me about two features of the car that make it more stable. So I told you that the greater surface area makes the car more stable. That was the feature. But they're now asking me the reasoning behind this. So the reasoning behind this would be that if this is like my floor and this is the object, at center of mass it's at this point, at this point. If I apply a force, if I apply a force and push this object to the right, what would happen is that it would start toppling over. toppling over. Since its center of mass was somewhere beneath this point, uh, just a second, let me redraw this. It would start toppling over. But the center of mass was some point over here. And since it's towards the left of the pivot, my drawing is getting a bit inaccurate. So let me just try it once again. So maybe this time, yeah. So my center of mass is at some point here. This center of mass is causing a moment which is like it's towards the left of the pivot, so it's causing a counterclockwise moment. So if I apply this force and this force causes this object to like move in this direction, the center of mass causes a moment which would be counterclockwise, opposite to what the moment we're causing, opposite to the moment caused by this force. So what would happen now is this counterclockwise moment would make this object turn back to its initial position. So that's one of these benefits of a wider shape. If the base was not wide enough, as in this case, as in the case of this square, so as soon as I moved it a little bit towards the right, the center of mass would have gone to the right of the pivot, and it would have toppled over towards the right. The moment would have been clockwise. So, like for example, if I do it here as well, if the force is a bit greater, so and the force manages to move the object to something like this. This time, the center of mass is at this point somewhere here, and it somehow suddenly has moved to the right of the pivot. And this time, the moment it is causing is clockwise. So the clockwise moment further facilitates the toppling over of this block. So that's why wider bases are there. Wider bases ensure that a greater force is required for the object to topple over. By a greater force, cause the pivot causes a counterclockwise moment, which tends to restore the object into its initial position. So that's like the detail about this. I hope this part is clear to everyone. So if anyone has any questions, feel free to ask them. Otherwise, this is all what we were supposed to do, and so we'll end the class. Okay, so I guess no questions. So then let's end for today, and hopefully we'll meet inshallah tomorrow. Same time, 8:30.